Okay, in this video we're going to take it from taking Riemann sums to approximate the area to actually finding the exact area under the curve. And we're going to start with a pretty easy example, but before we do that, let's take a look at what we have here. So what we have on the left hand side here is we have the summation symbol, and we're taking the function, multiplying it by delta x. And so if you kind of think about this intuitively, this first part of this is the function value, which is going to represent the height of our rectangles, and the delta x at the end is our widths. And remember that delta x, the formula for delta x, is just equal to the upper limit minus the lower limit divided by the number of rectangles that you choose to split it up into. And so if that number starts to approach infinity, then you're going to get such a small, the gaps are going to be smaller and smaller and smaller, and eventually it's going to look like a continuous area under there without any underestimation or overestimation. So so we come up with this technique here that it becomes just the integral right here from a to b. So we're going to take the antiderivative and then we're going to evaluate this. So here's a new concept that we're going to flirt with. So let's explain this by first taking a look at a simple linear function. So we have over here, we have 2x plus 1, and I've tried to graph it over here. And let's see if we want to know the area under the curve. We want to use, we just want to use geometry to do this. So if we look at the shape under here, let's find the area under the curve from, say, on the interval from 0 to, say, 3. And let's go ahead and mark that off on our graph, and let's see if we can identify the shape. So we have 1, 2, 3, and at 0 you can see the height of this is plus 1. So that height there is 1. And at 3, this thing has, let's see, 3 times 2 is 6, 6 plus 1 is 7. Sorry I didn't draw this to scale very well, but anyway, you can see there that the area under this curve looks like it forms a trapezoid, right? And the area would be all this in here. Okay, so let's go ahead and calculate that just using geometry. We don't really have to use Riemann sums because it is a solid geometric shape. So the area of the trapezoid is equal to 1/2 the base 1 plus the base 2 times the height. And remember, the parallel lines here form the bases. So the height of 1 is one base, and the height of 7 is the other base. So let's go ahead and put that in the formula here. We have 1/2 of 1 plus 7, and the height now becomes, let's see if we can erase some of this here. Whoops, didn't want to do that. The height becomes this horizontal piece, right? So basically we're turning this trapezoid over like this, well, we're not doing that, sorry. Anyway, so the height of this is equal to 3. So let's see what we can do here. So we have 8, half of 8 is 4, and 4 times 3 is 12. So the area underneath the curve is 12. Okay, so let's see if we can set up this integral formula and we're going to do it from 1 to 3. I don't know why I typed in 4 right here. Let me change that real quick. So here's our formula where we, and that should be 0. Sorry about that. So from 0 to 3. There we are. And so our function is this 2x plus 1. So let's just take a look at how we're going to solve this. So we're going to take the integral from 0 to 3, and the function is what? 2x plus 1 times dx. And if we take the antiderivative of this, we're going to get, you add 1 to the power. So you have 1 plus 1 up here. So you have 2x squared divided by 2 plus x. That's the integral, or the antiderivative. And usually we put our plus c right here, right? Well, now we have some specific values that we're going to look at, so we don't need the constant in there. So let's see how we're going to attack that. So what we typically do is write a little bar like this, and we're going to evaluate it from 0 to 3. And we haven't really defined what theorem this is that takes care of this, but I'm just going to show you what we're going to do. We're going to take our upper boundary, which is the biggest number, and we're going to subtract our lower boundary, which we have x equals 0 on this. So you just simply substitute that in. So let's simplify this, of course. This becomes x squared plus x. So we have x squared plus x, and we're going to look at it from 0 to 3. And we're just going to simply plug in 3 squared plus 3 minus the value of what? 0 squared plus 0. And this is going to give me 9 plus 3 minus 0. And in fact, that does equal 12. So in this simple linear equation, we were able to show geometrically exactly what the area was and then match it up with the integrals. So hopefully this will help you kind of relate how a Riemann sum and the integral are related. And we'll try a couple more examples in another video.